We published a paper back in 2016 where we gave mice rapamycin for 12 weeks from 20 to 23 months of age. So that's about the mouse equivalent of a 65-year-old person. We gave them rapamycin for 12 weeks and then we stopped the treatment. And we saw an increase in lifespan of, I think it was about 150 days. It was about a 60% increase in life expectancy from the end of the treatment. The biology of aging is something that can be modified. That's what people need to understand. Health is sort of a continuous variable, and we could think of it, if you just think of it on a scale from like 0 to 100, when you're young, you're probably pretty close to 100. I think most of us through our teenage years feel pretty bulletproof in our early 20s. And then over time, health gradually declines as we get older. But it's not a linear function. It's not a monotonically decreasing function. Your health can go up and down. Let's not worry so much about whether we call aging a disease or not. Let's worry about what are the things that we can measure, the functional declines that go along with aging, the biomarkers we can actually measure that we think have some predictive value for future health outcomes. Usually, the emphasis is on reacting to the disease. And what I mean by that is we typically wait until somebody gets sick before we do something about it. And then we try to cure the disease. And that's where the pharmaceutical development and research comes in. Really, most of it is aimed at curing individual diseases. Just think about the war on cancer, right? That's a great example of.
I've heard you use one term over and over again, and I have to say, I love the term. It's reactive disease care. Can you explain what you mean by this in the context of 20th century medicine and what you propose modern medicine should be concerned with?
So that phrase, reactive disease care, is really meant to refer to the fact that certainly over the last 50 years, and I would suggest even 150 years, our approach to health has really been focused on individual diseases in isolation. And that's true not only in the medical clinical community, but it's also true in the way pharmaceutical drugs are developed. It's also true in the way that basic biomedical research occurs. Really, the focus is on individual diseases, and we can all name the common killers in developed countries: cancer, dementia, heart disease, kidney disease. We can go down the list. But when you think about the way that medical professionals are trained or researchers are trained, in general, it's with a focus on thinking about a specific disease, and usually the emphasis is on reacting to the disease. And what I mean by that is we typically wait until somebody gets sick before we do something about it. And then we try to cure the disease. And that's where the pharmaceutical development and research comes in. Really, most of it is aimed at curing individual diseases. Just think about the war on cancer, right? That's a great example of how a very large fraction of the biomedical research effort in the United States was targeted towards an individual disease. Today, sort of a similar situation is in place with Alzheimer's disease. More than half of the budget of the National Institute on Aging is targeted directly towards Alzheimer's disease. Now, why is that important? There's really two reasons. One is, I think we would all agree that it would be better to keep people healthy rather than keep people sick. So if we could be proactive and prevent these diseases and functional declines from happening, or at least delay them, that would be a much better situation than waiting until people are sick before we try to do something about it. It's sort of like the difference between a preventative maintenance versus a repair shop mentality. The other reason why it's important is that all of these functional declines and diseases, or at least most of them that are the major causes of death and disability in developed countries, have at their root a single greatest risk factor, and that's the biology of aging. And so there actually is a path towards preventing or delaying these diseases by understanding that biology of aging and targeting it directly.
There are two terms that, if we can we define them today in as much as we can: a health span and lifespan. How do they differ?
Yeah, so lifespan's easy. So let's start with that one. There's really no ambiguity about what we mean. It's the length of time from birth till death. And that's nice in a sense because we can measure it, right? It's very quantitative. Health span is more tricky, and I've sort of gravitated away from the idea that health span is really something that we can measure at this point. So conceptually, health span is pretty easy, right? It's the period of life that's spent high functioning in good health. The challenge with that is those are qualitative terms. High functioning, good health are going to mean different things to different people. We don't have an agreed on way to measure health span. So the reason why I'm making this point is health span, in my view, really is not quantitative, meaning we don't have a way to measure it. And that's important because you'll hear people talk about how they have shown that if they do something or take some drug, they can extend health span. From a purely scientific, statistical, mathematical perspective, that's not true. Anytime anybody says they have shown that they can extend health span, that's not true, because in order to statistically show that you can increase or decrease something, you have to be able to measure it, and we can't measure health span. So what is a good way to think about health span? I think I would sort of frame it as the period of life spent high functioning, but I would also say maybe we need to move away from the idea that health span is something that we can measure, recognize that health is not binary. What I mean by that is you don't go from having good health one day to having no health the next day. Health is sort of a continuous variable, and we could think of it, if you just think of it on a scale from like 0 to 100, when you're young, you're probably pretty close to 100. You know, I think most of us through our teenage years feel pretty bulletproof in our early 20s. And then over time, health gradually declines as we get older. But it's not a linear function. It's not a monotonically decreasing function. Your health can go up and down. You may start exercising regularly and your health will improve. And so I think it's useful to think of health as a sort of continuous variable. And I'm going to get a little bit mathematic. So I apologize in advance if this is a little hard for people to follow. But if you think about a graph of this sort of health value as a function of age, maybe a better metric of health span is the area under that curve, right? So the longer you maintain high health, the better your health span is over your entire life. Then we can start to get towards something that we can measure. So I just think it's important for people to appreciate health span is really useful as a concept, right? We all want to increase the period of our life that's spent in good health. We just have to be careful when we talk about measuring health span.
You gave a very, very interesting statistic recently that if you were able to cure heart disease and all forms of cancer, you would only give the average person an extra 7 years of life because inevitably they would succumb to another age-related disease. That was quite astonishing for me to learn.
Yeah, so first of all, I'll say that really wasn't my work. That, and I think originally was done by a professor named J.L. Shansky, who's a demographer, and some of his colleagues. And that was based really on data collected by the United States Center for Disease Control, which is they're very good at telling and collecting information about what people die from, at least in the United States. And what Jay did was a pretty smart and pretty mathematically simple exercise, which was to simply ask the question, if we take out all the cancer deaths, what does that do to the life expectancy of a typical 50-year-old woman in the United States? And it turns out she gets about 3 years of added life expectancy. And it's about the same for heart disease, a little bit more, but not much. And then when you take both cancer and heart disease out of the equation, it ends up being about 7 years. And I agree with you. The first time I saw that data, I was kind of surprised as well. I thought that the effect, particularly from cancer, would be bigger. And intuitively, you would actually expect heart disease to be bigger because it's a higher frequency of deaths are due to heart disease. But because there's been so much emphasis on curing cancer for so long, and I alluded to the war on cancer earlier, 50 years of this, dedicated effort to cure cancer. But it turns out at the population level, the impact is relatively small. I do want to say one thing that's really important here. Curing individual cancers is really, really important. If you have a loved one, a wife, a mother, a father, a child who has cancer, you want that cancer cured. I'm not at all trying to minimize the importance of curing individual diseases in individual people. I just think it's really important to recognize at the population level, the impact of this sort of disease-first, disease-focused approach is much smaller than people typically recognize. And it's for exactly the reason you mentioned. It's because even if we take cancer out or we take heart disease out, you still have all of these other age-related diseases and functional declines that continue to increase exponentially as we get older. So if cancer doesn't get you and heart disease doesn't get you, Alzheimer's disease might, or influenza, or COVID-19 now, or kidney disease, and we can go down the list. Those things continue to increase exponentially so that the absolute magnitude of effect is relatively small.
I've heard some people in this space talk about aging itself being a disease. Now, is that too reductive? Is it inaccurate? Is it too crude?
Again, I think this is where definitions really become important. And so it kind of depends on what definition of disease you want to use. I tend to actually think that question is counterproductive, or at least answering that question is counterproductive, not because it's not important to think about aging as something that we can modify. This is, I think, the important point. The biology of aging is something that can be modified. That's what people need to understand. The reason why this emphasis on do we call aging a disease has become more popular is because there is this, I think, misplaced belief that if we define aging as a disease, suddenly the regulatory bodies like the US FDA are going to start approving drugs to target aging. That's not how FDA works. And unfortunately, well, fortunately, actually, I think it would be a mistake at this point. But I think that's where this argument kind of comes in. The problem is, as soon as you start asking that question, there are many people who immediately have a negative visceral reaction to calling aging a disease, right? Because then suddenly we're saying, no matter what your health status is, once you reach a certain age, you're sick. And I think that's the wrong way to think about it. So my view is, let's not worry so much about whether we call aging a disease or not. Let's worry about what are the things that we can measure, the functional declines that go along with aging, the biomarkers we can actually measure that we think have some predictive value for future health outcomes. Then those are quite useful for clinical trials where you could get FDA or other regulatory bodies to approve an intervention to target the biology of aging. It doesn't really matter from that perspective whether we call aging a disease or not. And so I think it's probably better not to worry about that. There are more important things that we could be worrying about.
You mentioned biological and biomarkers for aging there. What are they?
Yeah, so I mean, in principle, a biomarker of aging is anything you can measure that changes in a predictive way with chronological age. Okay, and I'm gonna make that explicit point. So we're just talking about your number of birthdays, and there are lots of them. So people tend to think when we start talking about biomarkers of aging that suddenly we are talking about molecular measures or cellular measures. It doesn't have to be. It turns out you can actually make pretty predictive chronological aging clocks just by facial imaging. So people have shown that if you take pictures of enough people, that artificial intelligence can actually pick out features of those pictures and with high precision tell you how old that person is within a couple of years. Now, intuitively, that actually makes a lot of sense, right? We all know we can kind of look at somebody and, with some level of precision, guess how old they are. And of course, artificial intelligence can do it better than most humans can. So that's a biomarker of aging, that collection of facial features that are predictive of how many birthdays you've had. The more but you can get molecular measures, and so really it's just anything you can measure that's predictive for age. Now, the more interesting question potentially is, can we identify biomarkers of biological aging? And this is where it's important to appreciate that your biological age doesn't necessarily have to equal your chronological age. So if you accept, which I do, and I think everybody should, because it's pretty much proven now that there is a biology of aging, then you should also understand that the rate at which an individual is aging biologically isn't necessarily going to be the same across all individuals. Some people will be aging biologically more quickly. Some people will be aging biologically more slowly. So biological age doesn't necessarily have to equal chronological age, the number of birthdays you've had. And the question is, can we find biomarkers there that are more predictive of biological age than chronological age? And the answer is yes. And there's been a lot of progress made in this space. I think it's a little bit early yet for those, what people are now calling biological age clocks, because they're not useful at this point. Meaning you can go, there's a bunch of companies out there selling biological age tests, and you can go take one of these and you can get a number that says your biological age is, I don't know, 37, but you're really 48. Okay, great. That's fantastic. What do you do about it? Or the other way around, you're 58 when you're chronologically 48. What do you do about it? There's no real actionable information from these tests right now. They're also not useful at predicting future health outcomes at this point. It can't tell you, okay, you're very likely to get cancer in the next 5 years or heart disease in the next 7 years. So they're of limited utility at this point, and the science is still very early. And I think it's a little bit unfortunate that there's been this rush to selling biological age clocks, this direct-to-consumer rush, because it's confused a lot of people, and the science is still very immature in this space. And the other thing I'll say about the consumer biological age clocks, if you're buying your biological age test from a company that's also trying to sell you a supplement, run away very, very quickly. I do not trust those companies.
You've been very critical about people and about companies taking advantage of the lack of knowledge in this particular age-related space. Can you tell us exactly where our current knowledge stands as far as aging is concerned, for sure?
Yeah, that's a tough question because I could probably go on for an hour trying to answer that. So let me see if I can give you just some bullet points. I think number one, which I've already alluded to, there is a biology of aging, okay? And we understand it to some extent. So within the field, if you go to any scientific conference, you'll see this slide that shows these things called the hallmarks of aging. In like half the talks, somebody will show that. Well, all the hallmarks of aging are 12 evolutionarily conserved processes or mechanisms that seem to be fundamentally important for determining the rate of biological aging across animals or within individuals. And the fact that these things exist, that we can put names to the hallmarks of aging, they're things like telomere shortening, cellular senescence, mitochondrial dysfunction. I could probably name 10 of them. I don't know if I could get all 12. But the fact that we understand the biology of aging enough to put names to these things is important, because that means that now in principle we can develop targeted therapeutics that modify the hallmarks of aging. So there is a biology of aging. We're starting to understand it. We've got some ways to measure it. That's where these biological aging clocks come in. It's still early, but we're getting there. And we know about a variety of different interventions that can modify the hallmarks of aging, that can, at least in laboratory animals, slow down or speed up the rate at which the animals are aging. And when we do that, we see the expected changes in lifespan and health span metrics. So if we use a drug like rapamycin, which is one of the drugs that I've studied extensively, that has been shown to slow aging across every animal where it's been tested, at least in the laboratory. And when we treat animals with rapamycin, we can make them live longer. We can increase average lifespan across the population, maximum lifespan across the population, and we can see improvements in function in pretty much every tissue and organ in the body, which is what we would expect if we've really slowed the aging process. So that's important. So that's kind of the state of the field right now. We know we can do this in laboratory animals. We can achieve, with rapamycin up to about a 30%, 25 to 30% increase in lifespan consistently. What we don't know yet is how easy that's going to be to translate into the real world. So the other thing I would say is we know that at least the hallmarks of aging are important for biological aging in humans and in companion animals, pet dogs, pet cats, as well as livestock living in the real world. So we know the same mechanisms, or at least some of them, are at play. What we don't know yet is whether these interventions like rapamycin will have the same effects outside of the laboratory as they do in the laboratory. And there's a variety of reasons for that. Laboratories are obviously very different environments. And so it's really important to answer that question. And that's kind of where we're at. There are now a lot of companies that have started up within the last 3-4 years in the longevity space that are starting to try to take some of these discoveries from the basic research world and bring them to market and go through the regulatory process. There's also the direct-to-consumer rush that I already alluded to. And so we'll find out, I think, in the next 5-10 years, at least for the first generation of what I would call geroscience interventions that target the biology of aging, we'll find out, do these things seem to work comparably in the real world as to what we've seen in the laboratory?
Rapamycin is fascinating, though, because it's not new. It's been around, about 15 or so years. And I suppose people listening to this now, and listening to you saying that mice can benefit from a 30% increase in their lifespan, they'll probably ask, why isn't this being used on humans?
Yeah, so I mean, rapamycin's actually been around for a lot longer than that. I think it was first discovered in the 70s on Easter Island. That's where the drug gets its name, Rapa Nui. And rapamycin has a super interesting history to it. So if people are interested, definitely encourage you to Google history of rapamycin. It's really fascinating. I don't have time to go through the whole thing, but after a series of twists and turns, about 20 years of sort of languishing in research limbo, rapamycin started being developed as an organ transplant drug, so what people would call an immunosuppressant. That's actually how it was first approved by the FDA, was to prevent kidney transplant rejection. So that led to it being sort of characterized and cataloged as an immune suppressant. And it was developed in parallel with some other much more potent immunosuppressants. And so it sort of got a bad reputation because of that developmental track that it went down. So it was used exclusively in the clinic as an organ transplant drug, where there are some side effects in that patient population who are also always taking other immunosuppressants. And so it got sort of a bad clinical reputation from the way it was developed and approved. It's since been approved for multiple other indications, including some rare forms of cancer, use in cardiac stents, and some diseases that are specific to the protein that rapamycin inhibits, which is called mTOR. So it's been approved for 4 or 5 different indications. And just for clarity, so that if people want to complain, they'll understand that I'm simplifying. There are other drugs in the same family as rapamycin that are called rapalogs, and I'm sort of lumping those all together. Biochemically, they work exactly the same way, so I think that's fair. In any case, so we know a lot about rapamycin use in people, but it's almost always in the context of this unique patient population who've had an organ transplant and are taking other immunosuppressants. The reason why that's important is because I think what we're learning now is that in people taking rapamycin who aren't organ transplant patients, who aren't taking other immunosuppressants, the side effect profile is much, much reduced. And it's almost, in my view, almost non-existent. I'm not going to say there's no side effects, but the side effects of rapamycin are much lower than the vast majority, again, this is my opinion at least, of other drugs that are out there taken pharmaceutically, and actually many over-the-counter medications. But you asked, why aren't we all taking rapamycin? I think there's 2 reasons. One is we don't actually know yet whether it's going to have the same effects in people for the biology of aging. And number 2, this reputation problem. So it's got a black box warning from FDA because of its use as an organ transplant drug. So the perceived risk of rapamycin, I believe, is much higher than the actual risk of rapamycin. And so I think that's going to have to be overcome before, even if we find out that rapamycin, has these fantastic effects on the biology of aging, health span metrics, potentially lifespan even, that reputation is going to have to be overcome, and that's going to take a while.
How many extra years could rapamycin give an average middle-aged person, for example?
Yeah, so I mean, again, I want to be very careful and say we don't know, first of all, that it's going to do that. And secondly, if it does, we don't really have any evidence that it's going to be sort of a linear extrapolation. So what I mean by that is mice on average will live about 3.5 years in the laboratory. So you could say, mice are about aging 25 to 30-fold more rapidly than people are. Okay. So if we just take that magnitude of rapamycin effect in mice that's been seen, and I'll just give a simple example. So in my lab, we published a paper back in 2016 where we gave mice rapamycin for 12 weeks. From 20 to 23 months of age. So that's about the mouse equivalent of a 65-year-old person. We gave them rapamycin for 12 weeks, and then we stopped the treatment. And we saw an increase in lifespan of, I think it was about 150 days. It was about a 60% increase in life expectancy from the end of the treatment. If you do a straight linear extrapolation, that 50-year-old woman we were talking about before, where you get 3 years from curing cancer, just a straight linear extrapolation would be about 2 decades from that kind of a rapamycin treatment. So again, my intuition is it's not going to be a linear extrapolation. It'll probably be less than that. But that's what the math tells us. If it were the case that it worked as well in people as it does in mice from a sort of rate of aging perspective. And in a typical 7-year-old mid to large size dog, we're probably talking a couple of years. So again, fairly significant increases in life expectancy are possible. Again, my intuition is that the lifespan effect will probably be smaller, but I think the health span effect might actually be bigger. And again, that's total speculation. I have almost 0 data to back it up, but that's my intuition.
You have plenty of data when it comes to taurine deficiency as a driver of anti-aging. Or as a driver of aging, I should say. I want to talk to you about taurine and about supplements in general.
The taurine story really, I have to say, is not primarily my work. My lab and I played a very small role in this study, but what this paper that was published fairly recently showed was that in multiple different organisms, including mice and some data from non-human primates and some data from humans, actually. With age, there seems to be a decrease in the availability of taurine in circulation in the body. And taurine is an amino acid, sulfur-based amino acid. So then the question, and that happens with lots of things. I think this is important for people to appreciate. There are lots and lots of things that show a change with age. And you can, again, we talked about facial features, but when you look at metabolites in the blood, there are a lot of things that change with age. So taurine is just one of them. The question then becomes, is that change that we see with age, in this case, a decline in taurine, important for the aging process or diseases of aging or functional declines that go along with aging? And the way you test that is you try to fix that change so that it doesn't happen, or that you restore the normal levels. And you ask, does that do anything to lifespan or health span metrics? And in the case of taurine, it did. And that's what makes it so interesting. So you could supplement mice with taurine and see that they lived longer and they seem to live healthier. So basically, you're restoring the levels of taurine back to what they would be in a young animal. And you see you get some changes in the aging process that looks like you've made things better. And again, there was some evidence in non-human primates, not lifespan, but some health span metrics to suggest that this may actually be true in primates, which of course, non-human primates are closer to people than mice are. So that's kind of the state of the story at this point. We don't really know whether or not supplementing with taurine in, say, dogs or cats or people would have similar benefits. Taurine is kind of nice because, unlike the case we talked about with rapamycin, there really isn't much in the way of safety concerns for taking taurine supplements. So I'm not recommending that people do it. Personally, I'm not taking taurine, but the downsides are pretty minimal. There's probably not much risk to taking a taurine supplement. I think what we need to do next is actually start to figure out, is it the case in general in people that there's a decline in the availability of taurine with age? Are there certain people that might be more likely to benefit from taurine supplementation than other people? And get at least some small clinical trials to give us an idea that, again, we're not going to look at lifespan, but you can look at some of these biomarkers of aging, some functional measures of aging, to assess whether or not taurine supplementation can improve age-related functions in people. But I'm pretty excited about this observation. I think there's a lot of potential there. And like I said, taurine is nice because you don't have so much in the way of concerns about risk. I also want to add, I think this is an area where, again, there's a bit of confusion, maybe is not exactly the right word, but a bit of sloppy thinking in this area around supplements and the idea that all supplements, because they're not regulated by the FDA, are therefore safe. There's a long history of things that have been marketed as supplements that were not regulated by FDA, and then we found out that they were harmful, and then FDA started regulating them. So I would just caution people not to assume that everything you can buy over the counter or on Amazon or whatever without a prescription is necessarily going to be safe. And in general, I know it's hard because it's hard to get good information, but trying to do sort of a risk-reward analysis for yourself, when you're thinking about all the things that you're trying to do for your own personal health, really try to think about a risk-reward analysis for yourself and, balance the appropriate risk with the appropriate reward.
Well, from supplementation then to nutrition and diet, I listened to your interview with Peter Attia, another medic and a very well-known podcaster in this space. And you talked at length about nutrition and about anti-aging diets. Can you give us your thoughts on this?
Sure. So again, I think it's really important to separate what we know from laboratory animals from what we think we know from human studies. So in laboratory mice, caloric restriction has been, I would say, the gold standard longevity intervention for many, many decades. This was first shown in the 1930s in rats, that you could extend lifespan by caloric restriction or protein restriction. And then that's since been studied, for the last 90 years in laboratory rodents. So that's the gold standard, caloric restriction. The thing that often doesn't get talked about with caloric restriction is it turns out that there's some percentage of genetic backgrounds that don't show a lifespan extension from caloric restriction. And there's some percentage that are actually shortened. Their lifespan, they're harmed by caloric restriction. So you will often see it presented in the popular media, and there are some scientists who unfortunately have written books on this, presented as if caloric restriction is, always this thing that we should strive for because it slows aging. The reality is, there are certain genotypes in mice whose lifespan is shortened by caloric restriction, and I am 100% certain there are certain genotypes in people who will be harmed by caloric restriction. So people should just be aware of that. And we don't really understand the mechanisms there, which means we can't really predict which mice or which people are going to be the ones that are harmed. So that's one thing to appreciate. The other thing to appreciate is there has been, in the last 10 years or so, this enthusiasm about what I would call alternative anti-aging diets, alternatives to caloric restriction. Because honestly, who wants to restrict their calories by 50% or 30% even? So things like intermittent fasting, time-restricted feeding, ketogenic diet. So the data there in laboratory animals is mixed. So ketogenic diet has a small positive effect on lifespan, but it's not very big. Intermittent fasting, when you don't calorically restrict, essentially does nothing to lifespan. At best, it's a tiny effect. And what I mean by that is you can intermittent fast. Let's think about people because it's easy. You could fast 2 days a week, right? That would be intermittent fasting. If you make up the calories you aren't eating on those 2 days of the week, on the other 5 days of the week, that would be isocaloric intermittent fasting. That does nothing for lifespan in mice. It probably does little to nothing for health span. This is where things get misrepresented. If you also calorically restrict the mice, you get a lifespan benefit in certain genotypes. So that's useful for people to understand that. And then time-restricted feeding, very little evidence in mice that it has beneficial effects. It's mixed at best and no lifespan benefit. So the question is, what about people? And here's where we just don't have enough data, right? You can find some evidence in the epidemiology that caloric restriction might be associated with relatively small effects on life expectancy. The best example of this, or one of the best examples, are the Okinawan Japanese, which historically ate about 15%, I think, fewer calories than mainland Japanese. They also had some differences in the composition of the diet, which makes it harder to tease apart. But they typically lived, 5 to 8 years longer than mainland Japanese. And so one interpretation might be it was the caloric restriction effect that led to that life expectancy difference. So that's kind of the best data we've got, or those kinds of data. I think there's no question. And here's sort of my takeaway. Okay, let me simplify now. I gave you a lot of data. Let me simplify. My takeaway is that if you are obese, that clearly puts you at higher risk for a whole bunch of age-related diseases, and it probably accelerates your biological aging process. If you are obese, caloric restriction in general is probably going to be beneficial as long as you're eating a healthy diet, right? So we have to be careful of malnutrition and things like that. But as long as you're getting all of your nutrients that you need and you're obese or overweight, caloric restriction is probably beneficial. Is that the same as what we see in mice on caloric restriction in terms of longevity? I don't know. We don't have an answer to that. And that's what the human clinical trials on caloric restriction have generally showed. If you take an obese or overweight population, you put them on caloric restriction, their biomarkers go in the right direction, in meaning that they appear to be healthier and appear to be potentially aging biologically at a slower rate. We don't know in healthy weight people whether caloric restriction would have the same effects. And my concern is that people are complicated, right? We're way more complicated than mice, including our social environment, our psychological state, the relationship with food that's complicated there. So I worry, and I've known a lot of people who've dabbled with a bunch of these anti-aging diets, and I've seen several of them develop characteristics that I would associate as a non-expert with eating disorders. And so I do worry that there are side effects in people to these, what I would call more extreme dietary regimens that you just need to be aware of, right? I'm not saying caloric restriction isn't right for you. I'm not saying the ketogenic diet isn't right for you. It might be, but you just need to be aware that a lot of these things, the psychological consequences, we can't model in laboratory animals, so we don't really know what the impact is. I know I've gone on a while, but the last thing I'll say about this, because I think also it's important in people, and we don't look at this in mice, and mice are very different in this regard, is the ability to maintain body composition, in particular lean mass with age. So we don't really look at sarcopenia so much in mice because they don't really develop sarcopenia to the extent that rats even do, or certainly not to the extent that people do with aging. I have real concerns with caloric restriction and some of these other nutritional strategies that are aimed at limiting calories, that unless people also implement some sort of resistance training protocol, you're going to see a pretty significant decline in lean mass. And in fact, we often see with people that undergo weight loss, an overall negative change in body composition. So what I mean by that is that when you lose weight very rapidly, you're going to lose fat mass for sure, but you're also going to lose lean mass. particularly if you're not doing something to maintain lean mass. And I think potentially that's a problem as people are getting older, because we know that the ability to maintain lean body mass and bone density, which also can be impacted by caloric restriction, are sort of fundamentally important in elderly people, right? Falls and fractures are really a major problem and actually a major killer. And so I think it's important to just be aware that if you're going to be doing something like caloric restriction, intermittent fasting, or these GLP-1 agonists, these anti-diabetes drugs that are now being used for obesity, that there's some thought put towards maintaining lean mass, maintaining bone mineral density. And I think, at least for now, resistance training is the best strategy to do that, in combination with these efforts to lose weight.
Terrific. So resistance training as opposed to, let's say, aerobic or cardio exercises.
Right. Exactly. Yeah. And I mean, the data are pretty clear that resistance training, so weight training, is more effective than cardiovascular training for building and maintaining lean mass, and then also bone mineral density, which I didn't talk about it as to the extent that probably I should have, because that's equally important, if not more important, than lean mass. The challenge with bone mineral density is that it's harder to fix. Once you've lost it, it's harder to get back. I think in terms of lean mass, there are things that people can do to regain the lean mass. And so, but I think paying attention to your bone density is super important. And again, this is my personal opinion. I think DEXAs are a really good tool for that. So maybe an annual DEXA scan to figure out where you're at, both for your lean mass and for your bone mineral density, so that you can track it and pay attention. And if you're seeing a decline, you can start to take steps to deal with it.
You have a company you're involved with called Optispan. Can you tell us about what work you do in this anti-aging space?
So Optispan is brand new. It's a brand new startup. We just closed our seed round, so that's exciting for us. And the word Optispan actually is two words: optimal health span. So what we call our BHAG, big, hairy, audacious goal, is optimal health spans for everyone. We really want to. So first of all, going back to the comment I made before about 20th century medicine, 21st century medicine. So we very much believe that the current reactive disease care structure in the United States and probably around the world is not sustainable, that it's going to fail, and that there are really a few paths that can go down. It could be catastrophic failure, which we're hoping to avoid, or it can be a gradual transition to more proactive healthcare, 21st century medicine, or as Peter Attia would say, medicine 3.0. What Optispan really wants to do is position ourselves to create tools that will help enable this transition from 20th century medicine to 21st century medicine. And so that includes things like developing protocols, identifying the best diagnostics. Some of these are more standard. I talked about DEXA. We talked a little bit about blood work, but also some of the cutting edge biological aging biomarkers, figuring out which of those are useful, which are most predictive for future health outcomes in people, and then creating a platform that will enable providers who want to make this transition to do it as easily as possible, to try to remove the friction from the system. So that's kind of a very high level overview, but it gives people an idea of what we're trying to do. We are staying very much away from direct to consumer for some of the reasons that I alluded to earlier. So our two domains that we're really focused on are corporate wellness and private practice. We think that actually corporations can play a big role in this transition to 21st century medicine. Right now, it's really the hospitals, primary care, and insurance companies that are really determining the quality of care that people are getting, at least in the United States. We think corporations can take a bigger role in enabling and encouraging their employees to get on a better health span trajectory. And so we want to make it easy and help companies do that.
Well, you're at the cutting edge of some very, very interesting and worthwhile and fascinating research and work. I wish you all the very best with your endeavors going forward. And can I thank you, Dr. Matt Kaeberlein, for joining me on the podcast today. Fascinating stuff.